Bench, and we are live. Let me wait a tiny bit to ensure that the audio is there, because it's probably one of the most important parts, so it takes a bit of time. And here we are back for the USB hub, probably maybe to the final one. And the last time okay, audio works. The last time we stopped was that the overcurrent sensing did not work. Well, it's not this anymore. USB hub. Oh, okay. So I had some bags in here. Version 1. Check on version 1. We had this overcurrent sensing circuit which didn't work. So this is a current limiter. And the idea is that either you tap after the current limiter, but actually when the current limits it doesn't drop too much, and it has issues starting because this is low, so the hub doesn't start, and here it didn't detect that there's any overcurrent, so there was no use for that. And I decided to change the chip and use a chip which is actually meant, so this was the MT something, MT9700. This was let's zoom a tiny bit more because we'll use this was useful because it is a single one, and you could set the values, the current limiting values, but the issue is that it didn't have a flag output or an overcurrent output, and now I change it and I received this part SY, just read it, and this should be capable of doing current sensing output. Well, current that it indicates when the current limit has been reached. It's, which part is it? This, nope, should be here, this part. So yeah, I received this part, and I'll put it in the USB hub and try if the current sensing works, because what we were able to do is have most. Why is it so dark? Can't highlight, because here it's quite bright. Can I? No, I don't know if I can increase the view. No, okay. Let's keep it this way. So V1 we don't need anymore. Deck. Here we have, oh, I still have plenty of them. Okay, that's good. Actually, these are new boards because the old board work actually, and I'm using it. Let me change. Let me switch to this. You see on the back here, this thing here. This is the USB hub with all 7 ports soldered, and this is now where. So it doesn't have the current limit sensing. It still has the current limit, so the chip is in there. It just doesn't have the sensing, so it will not switch off. You can still power on and off remotely. This works, at least for the 5 volts. For the 12 volts, I didn't try. And now my USB capture card and the power supply and the multimeter are connected to it. So let's see if it's more stable, because I started developing my own USB hub because the USB hub I found were not reliable, and I always had issues with the stream not connecting and so on. And it's been in use since the last video until now. Well, just after the last video, and it's quite stable. I'm really happy with it. But it doesn't have overcurrent sensing. So now I want to test the overcurrent sensing and fix this issue. And the last part would be to change to put a case around it. It's still very large. I could somehow reduce it, but I don't want to. I just want to small fix it, because changing every time to seven things is a bit annoying. And I wouldn't save too much space. So let's try it, and we will try this new mechanism. Oh, I actually also improved other things. The high voltage output has feedback protection, and the last thing is if there is but this is not implemented. This is drawn in the next version, because this is now version 2, and the next layout, this is already drawn in the layout. So if you download the source, but this is not in this version. This is still board version 1. So I will not implement it. I can still implement that by tricking. I removed the fuse also. Previously I had a 500 milliamp fuse before the current limiter. I removed it because there is already a current limiter, so no real need to do it. Although this is 600 milliamperes and not 500 milliamperes. I think it's okay. And yeah, the last thing I've added is that this is completely switched off if there is no high volt input. So if the 12 volts are not present, then this is switched off, so there will be no feedback inside, which is good because this means that everything you connect here wouldn't be able to feed back to the trigger to the other parts. I don't know if the target board is broken or not. So this is a security improvement. Or safety, yeah, both of things. But for now, I just want to implement that. But we need to solder the other parts, so we can do that. So let's do it, and then we can solder the first part. So this is the third time I solder the hub, or at least the second time. Yeah, the second time. Yeah, wrongly made. I need to switch him this way, and we will start with the upstream facing port with all the power parts and things like that, which are in this sheet. And yeah, you see it also on the screen on the side. You see here. Let's zoom it tiny. I can't zoom. Although we first do the power, so let's zoom it so you also have an overview of the schematic. Let's get the soldering iron started. Let's put this a bit more in the middle so you can see something. On the input there is still the 500 milliamp limit instead of a current instead of the current limiting switch. Also what I found out is that in the beginning there are a lot of capacitors which charge, and when I was enabling more than 5 boards at once, it would the current row was too high. It dipped the 5 volts and the 3 volts, and it reset the USB hub all the time. So the way I fixed it is adding a large capacitor on the 3 volt output. So this one doesn't reset so fast because there is kind of so this is not for decoupling. This is just for a storage of some unit in case the 5 volt dips a tiny bit. So we still have some energy. And this way it doesn't reset, and when it resets, it should recharge the capacitors, which we don't want. Then it would be an endless cycle. And I was a bit surprised, but yep, it's lots of capacitors. So hub, pen, and let's have a soldering session and maybe finish this. If this works, I'll probably make another one. So I have 2 USB hubs on my desktop as setup, and then one which I can play with for target boards. Or maybe I will order version. Yeah, I'll probably order version 2 before I make the third one. Let's just try to make this one work. Do we want to solder directly the huge parts? Yeah, let's do that. I still need to figure out where I've added them. Here. Yep, I've added the parts here. Then I have USB connector. This USB connector, and that's it for the beginning. The power is here, and in power I have plenty of things. I will need transistors. This is the MOSFET book. And resistors. Yeah, this is. I also need for the power input. Oh, the switching part. I think it's here. Transistors, drivers, probably. Or do I have other voltage regulator inductors? This box. This box includes the large ones. That's a bit for later. And resistors, I will just use my assembly tray. So let's get started. Up. Up. One, two. We'll first do the upstream facing port, and then we'll do the other ones. we'll do the dancing spring force one after another. So first the power. Let's try to tack this. Okay. And it's actually almost in place. This is not straight, this is straight. Up. Now I can also see what I'm doing. Up. I've never imagined that it would take so long to make, but yeah, I started this project 6 months ago. No, even more. Probably even more. But still, I did plenty of other projects. And it always takes time to get every time new parts that you order from China and not from the usual Western electronic distributor markets like DigiKey, Farnell, Mauser, and so on. It always takes 2 to 3 weeks to arrive, like the boards. So every time you want to make a change, yeah, you will have to wait 2 weeks. This is why it takes so long. Up. What is this garbage? Okay, now the USB port, so this I don't need anymore. Let's put it here. I think I still have some USB connectors. Nope, that's the wrong one. That's also the wrong one. Here. USB Type B receptacle. Hup. That fits quite nicely. Although the hole could, no, they can't be made smaller. Check. I know what I don't have anymore in which I refill. So let's solder this. I also soldered the shield, which actually works. Maybe this is what helps the stability because I have proper shield treatment. It's connected to ground through this resistor, and there is a decoupling capacitor, or decoupling, yeah, to filter the AC part out. And we'll also add them. And it flows inside. That's nice. You could even trim these studs, yeah, to have even better USB signals, because then you don't have kind of an end stub, which is not good for differential signaling. At least for high speed. Here we are just using USB 2. It probably won't matter. I'd still do it. At least we are aware of it. Now we can put, so in this sheet I've added J3, J2, J1. That's done. Let's add the shielding parts. Let's clean the tweezers first. Up. Because when you use them with flux, they get sticky. And you don't want them to stick to your parts. So I need 1K. Let's put some solder blobs on it. It's this one. And oh, this is a huge solder blob. And this one. Yeah, 1K could be less, it could be more. I don't know how to measure it. It must be something. That's all. I think 1K is fine. 1K 5%. In USB-C, this is solved. You have to connect directly the shield to the ground, and if you have a proper cable, it should already be done in the cable. In the USB-C cables, ground. Oh, sorry, that's not the wrong one. Ground should be tied to shield or tie in at both ends of the cable. So I think it's not a mistake to do it also on not USB-C but other parts. And 100 nano. And I think this is where I don't have 100 nano anymore. No, I don't. So let's get the MLCC. I really want to kind of heighten the... These are both okay, these are the same. On this camera, I want to change the exposure because it's a lot brighter here. How do I change the exposure? Record setup, scene. Is there a way to change the exposure? Fade, macro composition, shooting, no. Picture, even if we don't take picture, no. Setup, it's display date. Maybe if I press just exit. Function mic. Is there a way on this camera to change? Maybe. Wait. There are some other menus here. Prereq. Zoom. Wide. No. Nothing to change the exposure. Prereq, that's nothing. This is a lamp. That's not useful. This is just to zoom. So yeah, this camera doesn't allow you to change the exposure. Not automatic. Telemacro on. Oh, the macro is quite good. Telemacro off. Zoom. This is focus. What is this? This is where to make the focus. Nope. Nope. There's no. I don't know what this is. +1. Zoom. Nope. No. So you'll have it this way. It's a bit dark. I could change it in OBS. Okay. Let's not spend too much time on that. I need the filler thing. This thing. 100 nano X7F. Yep, that's the right one. And let's refill our tray. We can add more. We need so many of them. Oh, I just lost one. Not an issue. Up, cut the tape. That's done. That should be okay for a bit of time. So, $100 nano. Okay. Next one is D1. This is a diode, a TVS. I think this is in my diodes. Where is it? Where's my diodes book? It's probably in the MOSFETs. Yeah, MOSFETs, LED diodes. Here we have TVS. I think I need to order more of them. I still have some in the other bag. And maybe I should use this one, not the one in the book, because we'll need more than one. But the one in the SMD parts, LED SMD plus diodes, I think it's this one. Diode MOSFETs, no, it's this one. We'll also need a lot of MOSFETs, so up, let's lose this box and let's get the diodes, the parts going. We'll use this diode. We don't need the 4-bit, we need the 2 bits. It's this one. We'll also need the MOSFETs, these ones. And that's it for now. Ah, the small ones. This hotkey, no, that's STRBS. No, it's not the right one. No, there, and the diodes part. Okay. So, up. Pin 1 is here. Yep, that's okay. Next, so we did R1, we did C1, we did the TVS, which is somewhere here. That's done. Next is here, the fuse. This is in power. Up. This book. I want milliamp fuse. I'm sorry, put that up. And even during the dip, the fuse, actually the dip is caused by too much voltage getting drawn, but the fuse is not fast enough. So the fuse was not the culprit when I said I needed to add some capacitor. Okay. Plenty. Ferrite bead. Ah, we also have here ferrite beads, and here we have ferrite beads also. Normally I should have somewhere, I should have two here for the 12 volt, or is it the 5 volt output? Yeah, for the 5 volt input. The ferrite beads are also in my power book, I think. Ferrite beads, here they are. I need 4 of them. 1, 2, 3, 4. I also didn't stress test the hub I had. I didn't try what happens if you draw 3 amps and so on. We could do it with this one. Here is a ferrite bead, and here there is one. Up. One. Ooh. Should at least lay flat. 2. And now I'm powering using a 12-volt power supply. I didn't the hub I'm using. And this way I get really clean 5-volt outputs, which are really 5-volt. I think it should last. Can draw 3 amps out of it. Yeah, this board is getting old. It's not wetting that much. Oh, I also had... Oh, this will be a small rant. I did try... I'm living in Germany, and I did try to use a German prototyping in manufacturer. Board house. Just board house. I tried Eisler. And I'm really deceived by them. I find them bad. Seriously, I find them bad. I ordered... First, they want you to pay premium for having plated slots, which, I mean, every time you just use any of these connectors, any USB connector, any kind of connector, you have plated slots. And they want you to pay premium for that, which I find a bit weird, even if you don't use small tracers. So that's first. I know that was pre-order. During the order, I used the Blitz option, which makes you make the board really fast, but they only make the board, so it only takes 2 days to make the boards. That's quite fast, but it's only 2 days. The 2 days they start producing it only after 3 or 4 days, and in my case it was 3 days, 4 days, I don't know. But yeah, having Blitz and you have to wait 3 days or 4 days until it's 2 days. That's a bit weird. Still, it's fast. It was in Germany. And yeah, my first Blitz order, which I tried, well, they had 1 day delay. They weren't able to do it in 2 days like you buy it. They were friendly, is that they automatically reimburse you half of it, but it's still not a good impression you leave on me. If only in first order you're not capable to do it in Blitz, and that's weird. Okay, that was the order part. And then I received the board. One was wrapped, the other had scratches. The last one had silk markings, or silk smears. And they had mouse bites on the edges. Uncleaned mouse bites. I get it that you need to make panels and then to break them off. Although, if you do it properly, you route it afterwards. So you have clean edges. Okay, they have mouse bites. They didn't file them off. I needed a clean edge. There were mouse bites everywhere, and they not add 1 or 2. They had plenty of them. So that's annoying. And I had on-plated slots. They were not drilled at all. This is probably because you have to pay more to have plated slots. But if you don't have plated slots, it's unplated. The DRC didn't complain at all. The manufacturer didn't complain. There was nothing. So for me, it's manufactured. I looked again in drill files. They are there, the drill slots. I just didn't make it. And I contacted them to report quality complaints. No answer at all. So yeah, quite a small rant, but nothing went well with them. And it's my first order. So the boards are still there. They are not complete garbage. They're usable, but it's really bad. So no Eisler for me anymore. I can't recommend them. Really not. So that's it. Next part are here, the transistors. Or I should have talked while doing the work. Nah. Maybe I wasn't able to concentrate on both things at once. These are all PMOS charts, yeah. So these are these AP parts. 2, 3, 4. And also, like, you leave scratches and silk smears on your board. Don't you have quality control? And the advertisement is beautiful boards. These are not beautiful. Mouse bites, smears, and scratches? Come on. Can make better. Yep, not that beautiful. At least their website is. I liked how they listed the GRC rules. They were quite clear. That I liked. You had one picture with all the dimensions. That was good. And I like that they paid automatically something back when they have production delays. But yeah, you pay for the high price service, so you have so it's made quick. So if they don't respect it, it's the minimum that they pay you back. But at least you don't have to complain for that. Yep. And also the packaging. There was no bubble wrap. It was cellophane tape around the boards in a box. No wonder they're bent when they send them through the post this way, when they ship them this way. An advantage is that it fits in the letterbox and you don't have to pick them up at the post office. But still bad. It's not very straight, but it's straight enough. We'll add a lot of solder. It doesn't look nice. It's not right. You probably should do it when you reflow. It doesn't look super nice, but at least the solder is so thick that it will let a lot of current pass through. It's just an excuse. So, R2. What value does R2 have? R2 is 10K. 10K, we can put 5%. It doesn't have to be precise. 10K, 5%. Yeah. This one, 10K, 5%. Come on, wet. Okay. Let's have the marking in line with the silk. And let's solder on it. Dun, dun, dun. Up. That looks nice. And then the two, these two small diodes here, they're pain to solder. They're not to solder, but they're pain to figure out which one is the cathode. If we're in the resistor, let's finish the resistors. We have R4. R4 is 100K. Yep, I just filled 100K. 100K. It's this one. 100K, 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 R4. This one. I think this soldering iron has issues now. It's getting too warm at the handle. Don't know why. That's also old now. If you're wondering what it is, it's an OKE Medical PS90, something like that. So it's not the 13 megahertz, but the 900 kilohertz induction-based heater. So here there's an induction coil inside instead of a resistive coil. I don't know if it's necessary. I don't know what. In theory, the advantage is you can pump more energy. The one with just resistive element works pretty well. I think this technology is just to make it fancy. And also normally, yeah, when you put it in the stand, there should be magnets, or there are magnets, which should trip the head and then make that it doesn't warm. I think it's kind of broken. I don't know, because the magnets are broken, because they were too hot, and they lost the magnetism too much. But it doesn't get too much colder in the handle, in the stand. Okay, diodes. We need these super weird RBS types. Is this not? This is not my diode book. This was my power book. This is my diode book. I think these are Schottky diodes, right? Yep. Here they are. RBS. Yep. I need 2 of them. Yep, 2. 1 and 2. Tiny. And I also have been playing packaging, actually, or sending products. I recently released a product I was working on. Well, it was laying around during a conference. A French security conference, IT security conference. They presented an HDMI firewall. And so they did all the research. Nothing too complicated. You just cut the traces, mainly cut the traces and copy the edit information stored in the EEPROM. Still, a good device. The problem is that it wasn't kind of open source and available, and they decided, let's change that. So I re-implemented their research. I contacted them. They're quite happy that people that I was doing it, and there was no issue that I re-implemented. So I did re-implement it, and last year, then I just never completed the project. And when I was cleaning up my lab, I saw them in the box, and I said, it's time to finish it. So I completed the documentation and the schematics, having a proper release. I released it, and somehow it made it to the news. Well, the news, some hacker news, and I sold out within 1 day. And while I was making the documentation, I saw a lot of errors. Well, not of errors, a lot of things which could be improved, like the. Oh, and I also figured something out. This is kind of documented in the README or in the changelog. I had issues programming the EEPROM, but only with some kind of cables, with cheap HDMI cables. I don't know why. It just had red garbage and the programming didn't work correctly. And in the end, I figured that the cheap HDMI cables they skimp on the ground line. They just use the shield, which in the end, it shouldn't matter too much because the shield is, again, in HDMI connected directly to ground on the connector side, like with USB-C. So they're using the shield as ground line, and I wasn't using the shield as ground lane. I was just passing it through. So it means that I didn't have any ground. I wanted to use the ground connection. So this is one of the design I need to clean in the next revision, and then also this programming. I figured out that while I was documenting it, that programming the EEPROM is not that easy. Even with Linux skills, well, now it's a good documentation. Well, it's not too hard, but yeah, it's kind of painful. So there is a default profile, which is not perfect, but works with most of the cases. It does HD and supports very common format. But I have a programmer. I didn't, but the programmer, I decided in the next version just include the programmer inside it and improve it. So yeah, fix the ground issue, include the programmer, so you don't have this huge hassle of programming yourself, mainly because it's meant for end company end users, and they probably don't always have Linux or a guy using doing that. And yeah, I've ordered the next prototypes for the HDMI, so I can test the integrated programmer if it works correctly. Has to arrive, and then I will release it. But I was surprised. Within one day, I sold all my devices, which have been soldered by hand, not machine soldered. Next one is R3. This should be somewhere around here, 10K. And I think R6, which is next to it, yeah, it's 100K. Is it? Is it? Yes, 100K. That's 100K. So if you're looking for the HDMI, either, well, it's open source hardware, so you can re-implement it yourself, resolve it yourself, or just wait until I produced some. During 1 year, nobody was asking for it, so you can wait 1 month more. And also, the gadgets I sell, I don't make any profit out of it. It doesn't even cover the cost of the development, so it's more for fun that I'm selling stuff. 10K. For fun, and for me, for the not only for fun, for me to have the experience. How is it to sell things, to ship things? And now the shipping company just changed their policy and their rates, so I can't use them anymore. They canceled the international offer. It's a shame. I liked it. So now I have really expensive shipping. But I have no choice because the other offer is gone. Poof. I should have not soldered the through-hole parts, put it on the table, solder all the SMD, and then solder the through-hole afterwards. Yep. I can still do it, maybe. Let's see. Because they are on the edge. Let's try out, because this stand is getting on my nerves. Having to rotate it is not easy. So let's see. It's good if you do through hole, since now we do almost only SMD. Let's have it like, yeah, it works better. Let's have it, although it doesn't slide, but still works better. Good. Wobbly wobbly. Okay, and the next part is, so we all have the input parts, now the inductor, transformer, and so on. Oh, this is a transistor. What kind of transistor? So let's see. Up. We did, yes. This part is done. Now we're doing this part. Oh, a huge inductor. It should be in this box. These inductors, yeah. Inductors are heavy. It's almost a stone. Up. And I've seen the same. I didn't check. It's the first time I did switch mode power supply buck converter myself, and sometimes I see that they are using 45 microhenry instead of 33. I don't know why. I just use the recommended parts from the recommended values from the data sheet, and it works well. So, this soldering iron, oh, maybe it's warm enough. It had no issues right now. Let's try again. No. Ah, it did. Okay, it works. Let's see the other way around. Okay, it has issues. Yeah, can pump lots of power apparently normally, but the problem is that the temperature with these induction-based things, the temperature is just controlled by the Curie point of the metal, and so you have to buy for leaded, unleaded, or for the temperature. You have to change the tip. You cannot set the temperature. So you cannot put it a bit higher if you want to solder some larger things. In theory, it should put a lot of energy, but here it doesn't. And I need to use my other soldering iron where I can set the temperature higher and force it to have plenty of energy and to really go in fast in and out. Up. So let's put it for 390, and then if I heat the complete pad, it's always almost here. Maybe 380 is good enough. Night and day works so much better. Yep. The tip is also better for large surface soldering. Then next one, I think, so here we have a capacitor. Is it 1 or 10? Let's check. It's 1, huh? Just 1 microfarad. 1 microfarad, and it's the output, so it doesn't have to be a 50 volt 1 microfarad, right? Yep. This is 25 volts. Yep, it's 25 volts. Up one side. Flow. Ah, damn it, I just put solder inside. Let's try the desoldering pump and see if it works. Yep, works. Desoldering pumps work also for SMD parts. If you put too much solder and you're not able to remove it. C5, this is where it's a 50 volts. Yep. And capacitor here. I should have 1 microfarad and 50 volts. Don't have too many of them. Yeah, 100. They're more expensive. I could use a larger package though, they would be less expensive. I don't need to be that small, but yeah. I stopped doing 0805. Only 06, 03, and I don't think I will switch to 0402. At least not for my for boards I produce for myself. I still want to be able to repair and hack it correctly. And 0402 are a bit of pain. Still manageable to solder it, but and to fix it, but it's not as comfortable. Okay, I think this D4 is an SS33. Do I have them? Yep, I have it here. SS33. 3 ampere Schottky diode. Is it a Schottky diode? Yeah, Schottky barrier. Yeah. Did I just lose it? No, here it is. And at least here you can read where the cathode is. And yeah, I don't follow my solder guidelines. First the small parts, then the big parts. I have issues aligning it now because of the inductor just next to it. Solder on the pad. Is it on the pad? I don't think so. No, it is. Okay, that looks good. And the last part is, I think I put it in here. I hope so. Maybe not. Where is this voltage regulator? No. Where did I put it? In transistors. Do I have to look in my parts management? Where did I put it? So, up parts.qvoodoo.info. Tac, tac, tac. Step down. This one, power book. I put it in my book. It's a large part. Does it fit inside? Yeah, there it is. It is in my power book, so my power SMD book. There it is. So, buck converter fixed at 5 volts, and the 5 volts are quite precise. I'm happy with it. Let's solder pin 1. And this is the voltage regulator. Okay. Not perfectly aligned, but good enough. And now I need the soldering and the larger soldering iron for the last time for this huge tab. Flow, baby. Flow. Perfectly. Okay, let's switch off this soldering iron and put solder on it to keep the tip from rusting. And have it a longer shelf life. Well, shelf, it's not shelf because it's just lifespan. And that should be it. Okay. Now we also have these which enable it, so it's 10K. 10K, okay. 30, 10K, yeah. No, that's 20. Ooh. It's just to limit the current, but there's all sticking together, I think. There's kind of glue inside, glue. some flux. 5, 10K. Mm-hmm. And is this an NMOS? Yep, BSS 128. BSS 128, tiny NMOS. I can need more of them. It's just a signal to switches to invert the signal. Mm-hmm. Yep. Okay. Crystal is for later. The last one, this part. Okay, there's something wrong with this part. Where is C28? Ah, okay, this is the new schematic. In the new schematic, let me show you. So normally this part is 3 volts LDO. In the datasheet, it just tell you to add 1 microamp on both sides. That's okay for small applications. For such a large USB hub with lots of power, I added more. This is why I've added C28 and 29, and you see the numbers. It's just doesn't match to C2 and C3. This is I'm keeping the reference designator in the numbers, and then I'm just adding these 2 parts, and C30, and none of them are on this board. For now, it's just see the 1 microfarad, and I can change just to my microfarad with a 10 microfarad because you need the smaller one for faster switching, lower EMR. If you use a too large value, you can't regulate that well. Yep. That's 1. That's 2. And then was it on the input or it's on the output that I've added this capacitor. Up. Okay. This goes. Voltage regulator. I like these voltage regulators because they have a very, very tiny quiescent current. So when you don't draw anything, when everything is powered off, it just has a couple of microamps. While the other voltage regulator, like the AMS or LT1117, they have like a milliamp or something, or even more voltage on quiescent current. So huge. And to save power, it doesn't really help. So which one is it? This one. So yeah, they can't provide a lot of current, like the AMS is able to provide 1 amp, like that. This one is just 200 milliamp. For most of the things, it's enough. And here the 300 milliamps are only for, not only actually 200 milliamps. They are for this, for the hub, but also for all the LEDs. That's done, and I need a bigger capacitor. So now all the input voltages are there. Yep, so I'll add the capacitors. this one, and yet another one. So the first one, where are all my huge capacitors? Aluminium electrolytic, a box. So in the input is 470 at 50 volts, something like that, right? Let's cross what we did. We did this. Well, this we can't do. This also we can't. We did. What's happening with my pen? Why can't I draw? We did this. Yeah, we did this, but not these two ones. 470 at 50 volts. These are the largest one. And I don't have a lot of them. Huh? That's the bag. 470, 50 volts. Yep. I bend the leads. The wrong way around. Damn it, now I have to rebend the leads. Plus and minus. The part marking is on the plus. Yeah, good enough. Okay. Cut the leads and hold them, else they jump to your eye directly. They have a target programmed in. I call them eye leads. The ton on the output, we have 470 at 6 volts. So these are, what is this, 10, 100, 4.5, 4.7, 470 at 6 volts. Yep. See the size difference? Wait. I need two of them. Two. Yeah, I still have a couple of them. See? 470, 50 volts. 470, 3.6 volts. 6.3 volts. Huge difference. Up. So I need one here. Again, I mark the plus on my silk. Okay, now it's flat. Is it good to have it flat on the board? Should you add a bit of space so they can wiggle? I don't know. The board is quite rigid and big. It's 1.6 millimeters. I rarely do 1.6 millimeters board anymore. Although they are quite standard, if my product isn't big, I prefer them a bit smaller and lighter. 1.6 is just so huge, but for that they are really robust. And we need to add one here to the output. This is the output. Do I have another way to add it to the output? Because I don't want to add it this way. It will be in my way. I can add it this way. I'll probably add it this way. What is plus? What is ground? I think this is ground. So, hop. Let's have it this way. Yeah, let's try it this way. Can still cut the leads a tiny bit more. Check. I need to bend the leads. doesn't fit. Now it should fit. Hup. I hope this was right and this was wrong. Let's test it. So, continuity test. Okay, that works. And you don't see anything, do you? No, it's broken. But that was broken before, so it's not because of the USB hub. Let me restart it. Now it works. So continuity, beep beep. Ground. I think this is ground. Okay, that was the right thing. This is also ground. Okay, so it is correct. Now all the inputs are done. Let's test it. Oh, it's good that we... So let's test if there are shorts. Let's go back to resistance. And let's test the shorts. So this is the output. Here we have no shorts. Here we have no shorts. Does it work? Yes, it does work. And here we have 10K. Why do we have 10K? That's not a lot, 10K. Why do I have 10K between 5 volts and ground? Where do these come from? It's R3. Ah, yeah. I have 10K because this is shorted. Yeah. And V-bus is shorted to ground, so it's normal. When nothing is connected, I have a 10K aim load. Yeah. No, I think it's okay. So yeah, they're not shorted. Let's put some voltage on it and see how it behaves. USB I will need for the downstream facing ports, but for now I don't need. I need this plug and I need the crocodile plug, and let's start with the crocodile plugs. Crocodile. Here are the crocodile things. Let's go a bit higher. You are already seeing the the power supply. So that's fine. 1, 2, we put 5 volts. 5 volts, and we limit to 200 milliamp. Let's say 300. 300 is still fine. Let's get this USB thingy. A USB-B cable up. USB. This is plus. This is minus. Let's plug it into USB. And let's check out if it puts 3.3 volts. So no short, that's it. That's a good sign. 1 milliamp power usage, that's okay. Probably because of all the pull-ups, pull-downs and things like that. 1 milliamp is fine. Let's measure the output voltage and let's see if we have our 3.3 volts between this point and this point. And we do have 3.3 volts. So that works. Now let's do the same with the 12 volts output. For that I need the 12. Is it here? It's not here anymore. No. So if it's not here, it should be not here. Is it this one? Yeah, it is here. I was looking for the banana with these two leads. One. Two. Let's try the 5 volts first. Up. 1, 2. And if we put, does it feed back? No, it shouldn't. No, it should. So, oh yeah, again, I didn't put which is 5 volts. Let me write it. Pen. J2 is the 5 volts. 5 volts, this is 6 to 40 volts. It makes sense because it's next to this huge input capacitor rated for 50 volts. So, what we will try to do is see if on the USB side it will be fed back. So we will have a USB power meter. Let me get one up. Oh, I could measure actually the voltage. USB power meter. Tack. Now if I put 5 volts, it switches on. It doesn't use any power because we don't have the 10K. The one. This isn't on, so this is good. It's not feeding back through USB. We don't want it to feed back through USB. And if we test the 3.3 volt, it should have 3.3 volts. Yes. 5 volt input works. And it's not feeding back. Perfect. Now let's put it here. Again, it doesn't provide power here. So normally here, theoretically, this is more than 5 volts. It's 6 volts. Because we have the buck converter, and the buck converter needs a bit of a difference. I think 0 to 6 volt, depends on the diode. But in practice, you can put 5 volt in here. The advantage of putting 5 volt here is that you have 5 volt power outputs on these ports. So not only on USB, but also on the DC jacks. So if you want more than 600 milliamps from the USB, you can have 5 volt output here. And we'll see it in practice. So we have 5 volt going in. Now here we should have 3.3 volts, and we don't. I remember. This 5 volts only works if USB is plugged in. Well, it doesn't feed back, and now we want USB to be plugged in, so we will plug it here. We will switch on. Now we should have 3.3 volts. We do. And if we measure the output voltage of this thing, which is here, we see we have 4.9 volts, 4.8 volts. So yeah, if you put 5.1 volt, 5.1 volts instead of 6 volts here, you have 5 volt on the outputs. You have 5 volts here, so it's fine. Just put something like 5 volts. So okay, you have 5 volts always here because it goes directly from the input to here. It's already only switched to the MOSFET, but here. But on the USB ports, there will be a bit down regulation. You see, it's 4.9 volts. We can go until 4.78, 75 volts. USB allows it, so you can actually put 5 volts in here. But yeah, the power input works perfectly. Oh, it uses 19 milliamp. Maybe this is the quiescent current of this part. Yeah, might be. It's still a lot, but yeah. When you put high voltage, it's not a short, and we've seen it's regulated correctly. Maybe, does it feed back? I don't think so. Let's try and see. Here we have 5 volt 20. And this is weird. It's still drawing 19 milliamps. Although I disconnected this. Do we have the 3.3 volt output? Which theoretically we shouldn't have the 3.3 volt output. We do have it. Okay, is it a flaw? Why does it do that? If 5 volts are connected, we shouldn't have. This shouldn't be enabled, is it? Actually, it makes no sense. VBus here. Yeah, it means that this shouldn't be pulled high, it should be pulled low. Pulled low, it means that this shouldn't be fed. Why isn't it anymore? Okay, I have a flaw in my design. If we look at the sheet here, this switches, this NMOS switches this on and off. When voltage target is high, it's switched off. Is it active low? Only present, only enable when present. So it's active low. It seems to be active low. So if it's active low, the 100K should be sufficient, not 10K. Let's put 100K here, or something more than 10K, because when voltage trigger is high, it is no. This is active high. Because when VBus, when this is not plugged in, it is connected to ground. When this is connected to ground, since it's a NMOS, this goes through. So it's, let me get the data sheet. Is it active high or active low? Data sheets. EN pin, enable pin, drive pin low to turn on. So it's active low. So by default, it's pulled high by this voltage target. We could put 100K here instead of 10. Else we draw just current. So R500K. This is a really high impedance out input. Check the data sheets. EN startup. Yeah, 100K should be sufficient. Because else we have, when this is on, we have 40 volt going through 10K and we lose 5 milliamps, 40 milliamps through here, which we don't want to. So when this is, when USB is not, when VBus is not present, this should be put low. And if this is low, yeah, when VBus is not present, is VBus present now? Let's remeasure this. VBus is this one. VBus is at 4.2 volts. Who feeds back into VBus? Who feeds back into VBus? we have here, this is completely floating, so but this is pulled to ground, and this diode should prevent anything flowing through V-bus. So it's not here. We have this one also. Maybe it's this one is at fault. Voltage target. Now it goes to this part. Who feeds back the V-bus? These should be switched off. And when they are switched off, so here, prevent feedback. Yeah, I have Q4 to prevent feedback. Ah, I think I get, no. Okay, this was high at one point. No, but no, if... I think this is a circle. This was high at one point. Meaning this was enabled. Then there was feedback going here, and because this was high, it was always feeding through here. I think that's it, and this is why we have the 4.2 volts, because here we have the 0.6 volt drop, and I think that's the issue. We'll measure it. We have the 5 volts, and yeah, this is on, and this is okay. I have an issue here in my design. So the issue is, in the beginning it doesn't switch on. That's okay. Once we plug USB, V-bus is high. So when V-bus is high and the plug is in here, this goes high. When this goes high, it enables... Actually, it doesn't enable it. It should disable it. These are PMOS. So they should be disabled. What is the voltage at this point? So we have ground here and on R3. R3 is here. At one side we have 4.2 volts and the other side we have 3.5 volt. And I think the 3.5 volt is what is going to the MOSFETs. Yes, because it is put low. So we have 3 volts going to the MOSFETs. Then it goes, so this is the we don't care about this. At the end of D3, it's this one here, we have 3.3 volts. 3.3 volts are on Q3 and Q4, on these two. 4.4 volts. I think on this side, this is where the 5 volts are. It's probably still regulated at 5 volts. 3.3 volts. 4.2 volts. Wait, what's the output of the voltage regulator? 4.8. Why do we have 4.2? 4.8 volt is what's going out of the voltage regulator. It's on the 5 volt lines. And on the 5 volt line, it is pin 2, 1, 2 here. Here we should have 4.8 volts. Okay. Something is wrong. Ah, damn it. Oh. Maybe because the 4 volts are not. Let's switch it back to 5. Let's switch it back to 6 volts. So 6 volts input. Now we dropped a lot more. It's now using just 6 milliamp. Do we still have 5 volt on the output on VBus? Yep. Here we have 5 volt outputs. So we should have also 5 volt outputs right on Q3. Ah, it was the wrong one. Ah, I measured the wrong one. That's why. Pin 2. Here we have the 5 volts. Okay. So that's normal. And on the gate, which is pin 1. So we have 5 volts. It should be blocked, but we see it's not blocked because here is 4.7 volts. But since it's not 5 volts, this is blocked. If we look at here, it's not completely switched on. We have 3.5 volts on the gate. Yeah, that's a weird scenario. When you unplug USB, it doesn't switch off this thing. It feeds back in a loop. Why does it do so? So this is probably partially enabled, so it feeds back through VBus, because this is there, it enables it not completely. Yeah, I think it's because of that. So if we look at VBus, let's attach ground. Yep. If we look at VBus, it's here. It's 4.4 volts. This is because it's probably fed back from Q3. So in here, between the two of them, we have 4.7. That's a good clue. And then if we look at pin 2 here, 3.8. No, this is pin 1. This is pin 2. Here, 4.4. Yeah, that's VBus. And this is because this one is not switched off. It's 3.8 volts, so the MOSFET. So it is 1.2 volts lower, but it's at the threshold, so it probably switches on and off all the time. It doesn't switch off correctly. And because of that, yeah, it circles back around and it's not able to switch off correctly. Damn it. There's a tiny fault in my design, although it's a really corner case and it's not too important because we have no... Yeah, we do have feedback. No, we don't. We have 5 volts coming out of here, which we don't want to. It should completely be switched off. And if you put 5 volts back in, yeah, if we put 5 volt back in, we have what is, yeah, I can switch this off. Sorry, Aaron, don't need you anymore. If we have the 5 volts, this should be 0 volts, and it is 0, yeah, 0, because we have a 4 volt voltage drop backwards. But yeah, nothing is going through here. So it means it's not feeding back into VBus. That's good. But when I switch this off, I'm going back to 25 milliamps because it's not switching off correctly. See this? this part should be not at 3 volts, it should be at ground. But it's not. Let me get something to drink. And that's why it's probably oscillating. So I need to fix that. VBoss feedback. VBoss enable feedback. But I'll not do it for now. It's a small, tiny scenario. And it does feedback. See, it tries to go on and off. Here, this light blinks. And if I switch power on, then why doesn't it what the fuck? It was in power state. Yeah, it was. So it was feeding back. It was in sleep mode. But doesn't feedback. Okay. It feedbacks a tiny bit, maybe not enough for this to wake up, but it still feeds back, and we see it here. When it's disconnected, it shouldn't feed back. Okay, I need to fix this. Not today. For now, I only wanted to test the downstream facing port. So, and it's a corner case. When you unplug USB and you didn't plug this, I'll need to figure it out, but not for now. So, let's do, but else it works. Let's solder this part. These parts being the hub. Let's solder the hub. So we need hot air to solder the parts. Hub and flux. Up. Hot air, hot air. Hot air, microcontroller. 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 Here we have the USB hubs, and I should have 4 of them, and I will reuse as there's one I've already used. Yep, this one. I'll reuse this part, and this time it's not this one, it's this one. 3 of them remaining. Let's put it back. Tick, soldering iron is on, but I don't need the soldering iron. I need some flux. Flux everywhere. Underneath, let's get the hot air. Let's get solder on the pad. So pin 1, this time I don't want to make the same mistake. Pin 1 is here. This is 380. No, I need something like 400. 400 degrees. Okay, and it seems to be warm enough. Let's see. Not yet, but almost. Let's put a tiny bit of solder. Come on, you should wet. You should go through the whole on the whole pad. Help a tiny bit. It's still flowing, and let's put the QFN parts on there. And normally, if it's warm enough, it should lock itself into place. No. Doesn't. Okay, now it does. Let's have it aligned. Yep, it's locked into place. It did move back. And let's let it cool off. Now we can solder on the other side. Let's add some flux. The board is still warm. There's one pin which doesn't want to wet. Come on. Okay, this side looks nice. Next side. Okay, looks nice. This might be a short here. No. And the last one. Yep, looks nice. We'll have to test it. Let's clean it and let's verify. Where is my sponge here? Where is the alcohol? Tuk, 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 tuk. Oh, it's getting empty. Is pin 1 on pin 1? Yeah, at least this is correct. Now I need something. I don't want to get the microscope. I will use this. Does it work? Magnifier lens. Could work. No, it doesn't magnify enough for me. Nope. Have 15 times and 10 times. 10 times should be enough. So let's test, let's verify it. One side looks okay. Second side okay. Third side looks fine. Egg, I'm getting used to QFN. Yep, that all looks fine. I'm getting used to QFN. Now all the other things. Still a lot, so let's put some solder on the clock. Let's add the clock. I think it's an MCU. It's a 24 megahertz clock, right? Yep, 24 megahertz. Clock 1624. Pin 1 is this one. Although it doesn't matter, it's a symmetrical part. But let's still have pin 1 on pin 1. Well, it doesn't matter, it depends on how you make your footprints. And it's soldering iron, deck. Flux to get this refreshed. Well, it's not a bit, it's a lot. Okay, that's done. Too much solder here. Let's clean this off. And too much solder here. Okay. This needs 20 picofarads. So, and I'm sure it will also work with 18 picofarads. Now that I know what the issue was, but we have 20. 1, 2. That's 20. This solder is really getting warm. There's a real issue. The magnet is not working anymore. Okay, and the most important part, is that we need a mega ohm resistor between these two clock signals. This is what cost me a lot of time to get this out. And this is why my clock didn't work, and I'm sure now it works. It will work immediately once I've put everything else. And there are a lot of resistors, capacitors. So let's do that. So R14. I did 20 picofarad. Tap, tap, that's done, that's done. R14 is 100K, it's a pull up, pull down. 100K. Let me put some flux on the pads, no flux, some solder on the pads. And we'll do the EEPROM afterwards. C17. Let me cross. No, C17 is 100 nano. C20. Let me cross out things. 20 is 1 micro. Probably 16 is also 100 nano. Mm, 16 is 100 nano, yes. That's done. C9, 1. Okay, C8 is probably 100. C8 is 100. Yeah, R12 is 12 kilo at 1%. I'm blowing on the handle of the soldering iron. It's too warm. Do I have 12 in here? Yeah, 12k 1%. I do. It's really warm. C14. 100 nano? That's so far away. Yeah, probably didn't have the space to put it next, closer to the MCU. Well, yeah, to the hub. But it worked on the other hub, so seems fine. C15 is 1. I should have switched it. C14 should be the 100 and the 100 should be closer and the 1 should be further away. Yeah, I should have switched it around. I will probably. Let me write it. Switch C14, C15. Next. C19. 100 nano. C18 is probably also 100 nano. Yeah. I have the impression that in the stand the magnet does the opposite. It forces it to get higher because the handle is super warm. Oh, I didn't put it. This will be afterwards. So let's finish this side. C11. 1. I'm getting out of 1 microfarad. C10 and 100. C21 is 21 100s again. C22 is 1. And it's my last 1 microfarad. Now, the EEPROM part. I'll put the header last. So all this part, and then we can test if the hub works, and then finally we can concentrate on the downstream basic port. Finally, it's getting warm in here also. Switch on my fan. Better. Whew. No, you can't hear it. Okay, that's good. You can't hear it. So the EEPROM, we did probably all these capacitors, almost all. We didn't probably do this one. So let's put solar bulbs. Okay, tack, 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 tack. And this. I have plenty of capacitors actually. C23 is... What is C23? Ah, it's for VBus, it's 100 nano. So it's not a decoupling capacitor. Just to have a smooth VBus input. Although maybe you could still then call decoupling capacitors, but... Ah, this handle! Then we have R10. R10 is 1K. 1K, it's inline, right? 5% is enough. I don't need 1%. Else I would have written it in the schematic if it's 1%. So yeah, by default it's, if I don't write right percent, 1% less, you can use 5%. But now I'm buying only parts with 5%. I still have stock, 5% stock, but everything I buy now is 1%. And not that much cheaper, that much more expensive, and at least I don't need 2 stock parts, and then we need 100K. But I need to empty my stock first. That's 100K. Okay. C13. Which one is it? 1 microfarad. I don't have my 1 microfarad anymore. Let me get some. 1 microfarad. Okay, I have plenty of them. Oh, somebody is calling me. I need to take this. Bench, and I am back. Okay. Yeah, we were soldering these parts, and the handle is very warm. We were at C13. C13 was 1 micro, and this is what I was filling, right? Yes, I didn't fill it. So let's fill the 1 micro. Up. 1 micro is filled again. And let's switch the fan back on. I'm dying here, it's getting warm. How is it? 31 degrees. And it's warm. C12 is 100 nano, I imagine. Yeah, C12 is 100. This is not flat. I'd like this piece to be flat. No, it's flat. Then we have... What are these resistors? Here. C24, R15. R15 is 100K. Okay, let's put it the right way around. And C24 is probably the one. No, that's something else. That's also that's a to stabilize reset. Not sure if it's really required, but it's good measure. Probably from one of the guidelines. Okay. Now we have R22. These are all 4.7K. This is for the I2C bus. 4.7K. R13. That's this. No, there's something else. R13. That's 100K. This is yet not for the I2C, but still for the hub. And then the EEPROM. The EEPROM is in my. Here I see book. Where is the EEPROM? EEPROM. I should use this SAT EEPROM. I still have so many of them. SAT, psych. The one I'm using here is SAT. It's small, and this board doesn't need to be small. It has plenty of space, so I could actually use a larger EEPROM and have plenty of space around here and somewhere around here, so I could use the larger one. Maybe on the next design. C25, it's probably 100 nano, right? Yeah, for the EEPROM, 100 nano decoupling is okay. That's fine. And then the two last resistors are for the 7K. One and last one. And then we're complete with complete upstream facing port. We need to flush the EEPROM. Okay. This is done. I don't want to solder. Let's check. Somehow I don't want to solder this pin header in, but I can only do that if I have enough Fogo pin. No, I don't. Although I could make the same thing, like this kind of device with 6 pins, and then you can plug in. Let's make that female headers. I'll use this should be 6, 2, 5, 6. That's okay. And pogo pins. Where are my pogo pin probes? Pogo pins. Probably. Still hope I have enough of them. Pogo pins, and I'm using, I think, P75E2. Isn't the right one? It's the largest one. Yeah, these ones. Do they fit in? No, let's see if I have. Oh, we have even one who bites in, but now P75 is correct. Let's try to fit them in with the tweezers. Yeah. This way they fit in. Yep. Bit too much though. Chup chup. Yeah, it's not ideal. 1, 2, 3, 4, 5, and 6. Yeah. I hope it does make contact. Ah, you're not seeing what I'm doing. I'm just inserting pogo pins into this female header thingy. Up. I don't want to solder. I don't want to solder a pinhead on there because it stands out too much, and I want it to fit in the case, which should be as flat as possible. So yeah, works probably good enough. Wink wink. Let's try to flash the EEPROM. And then we'll clean the board. A flash programmer. I'll not show you, except if it takes longer than expected. I don't hope so. So, USB. I also need USB to power the hub, else it will complain. And I need to change. Let's put it here. Let's have it here. I did have, where is it? In my USB hub, I did make a cable especially for that. Yeah. This is pin 1. Hub. Where is the pogo pin header now? Damn it. Lost it. Damn it. I lost the pogo pin header. Here. Up. Up. Okay, we can close this. We can close this. At least I can show you what I'm doing. Screen? No. Full screen. Yep. Project, USB hub. The EEPROM is in here. EEPROM, and then I also have officially now USB ID. And so what I need to change is the version. So I also modify the script. Let's put it this way so you can see it better. USB hub. So yeah, I've corrected this. So I've allocated a USB ID from the OpenMoko project. Requested one, you just need needs to be open source. In my case, it's open source hardware. There's no firmware. Only in the configuration. I'm not sure if it's firmware. And what I changed, I fixed these max power. This is done. The important things I changed. Where are all the? How is it? Over current, individual port by port current sensing. Okay. Auto switching, and we had also port by port. How is it called? Yeah, but current sensing. Well, that's it. Current sensing. Okay, that's that. So it is port by port. That's okay. Power control, individual port by port. That's fixed. And then in the script, I've added the manufacturer strings, QVoodoo, power USB hub, and I need to change the serial. The serial is the date. 2024 606 30, and this is the first one. String length. Serial string length. Does it have to be fixed? I think that's the address. Yeah, that's the address of the length. And now, if I plug this here and I hold it correctly, we should be able to program it. EEPROM, come on. I played a lot with EEPROM. Yeah, this is from my I2C and for the USB hub. Mini Pro, yeah, this. Okay, verification, okay. I was able to write it to verify it, means that the pogo ping thing works. And now, journal control -F. Yep, it is there. Insufficient power, that's normal because I only power it over the USB port, which is 500 milliamps, and I say that every downstream port can have 500 milliamps. So it reports that. So this is correct. Flashing works perfectly. The USB hub is there. Let's clean it. Let me switch back to the bench. This is the bench. Let's clean it and let's make the downstream facing port. And I forgot to change that so you were not seeing the schematic. Well, I wasn't either. Hub, plenty of alcohol, although it's almost empty. Let it soak a bit, and a small trick. So I mentioned these wipes. So these are lint-free wipes from manufacturing when you make your nails, and they're quite good. They still leave some residue. What I also found, which doesn't leave too much residue, is these foam things. I don't know how they're called, but they're open bubble foam, and they absorb the liquid and the traces, and it works super well to clean boards. You can't rub it as strong as with the wipes, but seriously, it removes all the residues. and yeah, I can recommend it. And then you have this thing, but you can cut it off using a scissor. I don't know how this foam thing is called, and that's it. Then you have open parts again, and you can continue cleaning. So to clean off boards, yeah, good tip. These foam things, I don't know how they're called though, but you buy them in very large. They are cut, and it's super inexpensive. The USB is kind of clean. It's not very clean. Oh, I didn't clean this part at all, so I didn't. I thought I did already. Up. And what's good is that sometimes with these wipes, for example, when they have sharp things, it still remains some filaments. It's not like lint here, like on this sharp part. And with this one, it breaks off the foam, but when you blow on it, you actually remove it. Looks clean enough. Let's make the downstream facing port. Up. So, pogo pins, I don't need them anymore. Yeah, I have enough of them. Should I order more? No, I should. I have enough of them. Let's start with from top to bottom. So, what we want, we will cheat. This is where we will modify, because we will kind of implement this schematic, which I will put actually in the screen so you can see it on the old board. So I need the old schematic also to figure out how to do it. We want to implement this right now. What we first need to do is some kind of to bridge the fuse. I will not use the fuse. Let's use a resistor. Oh, a 0 ohm resistor? But they are only 100 milliamps. So I cannot use a 0 ohm resistor, except if I have larger ones, but I don't think so. What we can use is just... up. Let's use the resistor. We can focus more, since we will only focus on this part. Yeah, next time I want to figure out, I'll probably make an extreme why this heats up so much. Or just switch to the next iron, I don't know. And on the other side. So this is our fuse now. Tack. Then we have... I can't put it more. I don't need this one. It's not important. This is important though. This is 10 microfarad. 10 microfarad here. The resistor is not important anymore, because the resistor, I think, I need to get the old schematic. Get the old data sheets. Oh, no, I wanted to do it on the capacitor. That's the capacitor. Check. Check. Okay, that's the capacitor. Now, how was it working? What was... yes, what R103 was for the resistor. Now, let me get the schematic of V1. Do have one which is not... yep, this one. So here we had this resistor on pin 3, which was the set resistor to set the current, the limiting current, to 560 milliamps at that point. Now we don't have this. This is the output flag. So we will have to connect OCS here, right? Yeah, OCS on pin 3. This signal, and this signal is on these two diodes. And this is what we will do using the resistor again. So pin 3, it's here. There's no convenient way, but we'll do it this way. So we'll put, this is OCS. And it will go here. Can we short? No, we can't. This way. Yeah, that's how you're doing it. I could use some proper magnet wire, but this will be fine. And it looks nice. It looks like a budge. Which it is. Damn it. Okay, now we need this power regulator, I think. Yep, this one. Yep. We need one. Okay, that's done. And we can solder the rest. So we have, that's the fuse, R101. It's 1K. 1K. I need to put some solder first on the pads. Damn it. Something attacked me. Solder blob. And the 3 LEDs. 1, 2, and 3. Good enough. Under it is R106. R106 is... Which one is it? Ah, it's not there anymore. Damn it. Where is this old thing? Here. Which one? 106. Oh, it was for the LEDs. Why is it there? Oh, it is there. 1K. Then 102. This is 100K. What is below it? 105 probably. And it's probably also 100K. 105. Two, 103, 104. Where's 105? Ah, it's the green. It's the green light. Yeah, I will put 10K. Even the 7K I added is just 1K green. I didn't fix it. I put 10K on green. The green is super efficient, super bright. And it's the power on LED. So it's always on. Far too bright. 10K for you. Okay. C102, that's probably 10 microfarad on the output. Yeah. Okay. All these parts, 107, and they are both 100K. Wow, 100K? Yeah, it's okay, it's okay. Yeah, it worked for the other, so. Although I never tried switching on and off the 12-volt output. 100K. $100K and $200K. Yep. Now one is a PMOS, one is an NMOS, and I have one of them here. So the 103 is this NMOS, the small signal to invert the signal. And the other one is the PMOS. So tiny PMOS able to switch a couple of amps. Now it's time to put the LEDs. We have, I think this is green, red and blue. Is it? So where are the LED numbers? D106? No, that's something else here. D103. 103 is, yep, it's the green one. Ah, I don't have any. Oh, I have one green LED. Yeah. If I want the other hubs, I need to restock. Up. Up. That's green. And I put it the wrong way around. Come on, unsolder, I don't want. Second soldering iron. Up. And there we have it. I smear on this. Desoldering pump up. Okay, that's cleaned. The LED is still here. Let's put it the right way around this time. Doesn't, it's not straight at all. Switch on the iron. Let's add some flux. Now it's straight on. And it's the right way around. The second one is 102. 102 is the red one. Red. Then the last one is blue. It's this way around. And then we have, oh no, there's the TVS, output TVS diode, which we need to add. Could use also, yeah, this is more production board now. Well, production. A serious board, else I could use pink LEDs. I ordered some UV LEDs, but they turn out to be pink. I don't know how they put them as UV LEDs. Weird. So, TVS diode, you come here. Damn it, I lost it. Did I lose it? I think it's gone. No, it's here. My solder back. Okay. Now the 100 microfarad capacitor, nanofarad, sorry, capacitor for the shield. For the high frequency noise, because else it is connected through the 1K again to ground. But everything which is AC can go through this 100 nanofarad. Looks fine. Now let's put a DC barrel jack. No, let's put the switch first. Switch is here. And I will keep these switches, but I did get some samples of other switches, like push-pull switches, SMT, but these are really useful because you can feel them more than, and then you don't have to press on the board, and they're not too hard to solder, so I will keep these switches. You just have to solder in before you solder the two other parts. And it's easier to see the push-push. You never know, you cannot see that if it's on and off. Here with the position you can clearly see it, and here I will not be able to pass through because there is solder in the hole. Solder in the hole. This is the barrel. Damn it. Okay, and now the USB ports, and I think it's in my USB box here. And which one is it? So many USB connectors. This one, yeah. Up. This way around. I need to tag 1 point U. And now I can solder the other ones. That's it. Now we have the capacitors. We have one time the 6-volt capacitors, which is 150, and then the other one is 100. Where are the capacitors? Here. This is 150, and this is 16 volts. Yeah, that's fine. Then I need the 150 volts. These ones. Yep. And then we can try our hub and detect if and test if the overcurrent sensing works. Which is the point? Oh, which one is it? This is 50 volts. Yeah, it goes in here. Last one. This way. Okay, let's clip the leads. And because I'm sure everything will work right, let's clean it. Plop, 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 plop. Okay, so now we can test if the short circuit situation is solved. How do we do it? We will provide 5 volts. We will short and we will see if the power LED should be on. Well, edge is on, center off. Okay. But I think nothing is on if there is no USB power on the USB. So let's put power on the USB. Actually, we could put the whole power through USB. We don't need the 5 volts, but the 5 volts is useful because we can monitor it using the power. This, and let's see if it still works. No, it doesn't. Okay, so my software has issues. And I need to restart it. Oh, okay, yeah, it has issues. But it doesn't say inactivity. Why doesn't it say inactivity? Huh. Huh. There should be a timeout. So now I'm watching at my DMM. And normally after 3 seconds, if there's no new measurement, it says inactivity. Here it doesn't. And then it should restart the H-top. And nothing is at 100%. It's just OBS, which uses a lot because it does the encoding. So I don't know what the error is. Just restart it. Now 5 volts, 1 amp, which is 5 volts. This is 5 volts. Here we have USB. Let's connect USB. Tac. Switch on. Nothing is, the USB is not on because, well, the hub is not on because USB is not on, and now it should be on, but it's not. What? Is there a short somewhere? There's something wrong. There's definitely something wrong. Ah, no, it's just the power is not enabled. Okay. So it was reading. Ah, here there's feedback. Ah, but that's not too important if there's feedback here when it is connected. Now we switch this on. Okay, the output is on here, and if we switch this on, the USB should be on, but it's, nope. Nope. So this is off, and it doesn't switch on. It doesn't switch on. Let's test if we connect over the USB. What USB tells us. So when we connect it, let me show you full screen. When we connect it, okay, 7-port detected. And maybe the hub needs to be initialized. That's possible. It's completely, entirely possible. My laptop is getting warm. So let me switch back to the bench. Bench. Now there we have it. Here we have the output. We can switch it on and off, meaning that it doesn't report any overcurrent. And I'll put the thing back. I'll put the journal here so you can see journal control -F. What's happening? And I provide power externally. 5 volt is this one. Check. Use the 100 milliamp, probably just to charge or to restart. That works. Now it uses only 1 milliamp. Seems suspicious. It's just one LED. Still, it's 10K and still bright enough. Normally over USB it shouldn't use any power. We tried that already. Switch this off, and now what happens if we short it? Normally this should be switched off and we should have a report on the journal that this is shorted. So let's try it out. Tack, let's get something to short. Lustum, and let's get the moment of truth. Tack. Oh yeah. Did it report anything? No, it didn't. Maybe because it takes longer. Okay, it did switch off, but theoretically it should report back to the host that there's an overcurrent situation. Maybe it doesn't report. Ah, and now it tries to restart. Retime. Ah. Yeah. At least recovery works. How much? Ah, it uses 200 milliamp, 500 milliamps. Yeah. 200 milliamps. And then 500 milliamps. So this tries to recover by itself. But 200 milliamps, this is not what we expect. And the chip is getting warm. This hub is getting warm. I need to test the OC. I need to see the signal. I think there's still an issue. Damn it. I thought this would solve everything, but it doesn't. So we need ground. This is ground. Oh, it's not. This is ground. If we have a look at the OCS signal, 2.5 volt, it should be 3.3 volts. I need to put to add a pull up there. I can actually. Here is a resistor. Let's put a pull up. Let's switch off power. Let's disconnect the USB. And let's add a pull up. How much? Let's put 10K. $100K is probably not enough because it will change and it doesn't pull off enough. So let's put 10K. You're in the way. Oh, is this ground? Was this ground? That's your data sheet. It's 103. Oh, it's ground. it's not 5 volts, so I can't put it here. But I can notice this to 5 volts. I need to put it up to 3.3 volts. Where do we have 3.3 volt on this board? Somewhere on the LED, I think. No, also not. There should be a 3.3 volt somewhere. $3.3 volts on the blue LED. I think this one. It's across the two LEDs. It's here, 3.3 volts. So I need 10K, but as a through-hole resistor. 10K. Up. This is 3.3 volt, right? And it's... no, it's not. Either this one is or this one is. This one is 3.3 volts. And we can measure it. Yep. Switch on. I have a crocodile somewhere. So you're connecting the minus from the multimeter. Now you're connected. Here, is it 3.3 volts? Yes. So we found it. Up. Let's put the 10K on 3.3 volts. And up to this line. Could hide it a bit better. It's in front of the LED right now. Up. Let's pull it up. Normally it's pulled up by the hub already, but the signal was a bit low. 2.5 volts max, not what I call high signal. So switch this on. Plug in the power. Deck. This works. Okay, let's measure the voltage on OCS now. 3.3 volt looks better. So it needs a pull-up. That I didn't know and I didn't add, but I will. We have place for a resistor right here, so I'll add 3.3 volts. And now if I short, here is the shorting lead. So this should go down if I short. It doesn't. This should be pulled down by this. I mean, we're only using 200 milliamps and not 600. So there's something going on right here which I don't understand. Let's disconnect this. Okay, it switches everything off. If I just connect a normal USB, I think it doesn't go on, right? I want to see how much it uses over. No, it doesn't. Over USB. Yeah. No, this is protected. It's fine if it's protected. Check. I have to enable it. Up. Okay, so it uses nothing when 5 volt is you don't see it here. It uses nothing when there's no short. So when there's a short, check. It still uses nothing, and this only uses 200 milliamp. There's a short though. It should use more than 200. It should use 900 milliamps. Or that's weird. How does this current limit work? And it doesn't say, does it? Well, this one. It doesn't say that there's a short. But also if we set the output voltage 0 volts. And here on the input, 5 volts. What does this chip do? What is this chip doing? It's limiting to 200 milliamp, but now 300, and it's never saying that there's a short. What does this chip do? I did solder the right one. This one, what's the marking on it? Yes? CV0UD. CV0UD or CVD, CVQOD. Okay. So let's have a look at its datasheet. I don't understand what it's doing. Let me wash my hands. Because we have finished with soldering. Sure, time to read the datasheet. And at least it's normal that it doesn't report. This is the EEPROM, we're finished with that. Datasheet. It is which part? Current limit, this one. I ordered the right one. SY6288, SY6288, and then I have the AAAC. This one, this is the right package type, active high. That's okay. Is my footprint correct? 1 is the output, yes. 2 is ground, yes. 3 is OCP, that's correct. 4 is enable, yes. 5 is voltage input, that's everything correct. So I did, my schematic is correct. Ultra low RDS on, switch with current limiting function to protect the power source over current or short circuit. This is clearly a short circuit, which what we did. Fault flag, output for current and fault condition. That's what we did. Yeah, so pulled up. Okay, it needs to be pulled up. How does it say? 10 to 100. Okay, then I will put 100. It depends on the signal. I will still put 10K just to be sure. Well, let's see. And normally in the datasheet of this, the OCS signal is pulled up. Pin description, pin table, pin configuration here. Okay, then we need to go to pin description. Where is overcurrent? Overcurrent here. Contains internal pull-up. So I don't need an external pull-up. To 3.3 volt supply. I don't need. I'll try to remove it to see. Once we manage to have it working, to see what's going on. So yeah, 10 microfarad, that's what I added. I also have on the output 10 micro and 150. Yep, that's correct. So I have this application circuit, exactly the same. And well, and this is the part. CV, yeah, that's what I said. And this year code, okay, lot number. Open drain, okay. And then it should pull it low. We are active high, we have an output, so this is correct. What is happening? Why doesn't this chip work? Or is something which I didn't understand? Current limit between 06. That's electrical 06. Normally, well, the current limit is 0.6 amp. And is it written somewhere else? No, yeah, here. 0.6 amp. We have the A, the first A, optional spec code. So I did everything correct. Why don't you trigger when you have a short? That's your only purpose. Do I need to switch on the oscilloscope? Current limits. That's weird, because here we have the A, and it says it's between 0.8 and 1.6. We have 0.6, normally it's 0.6 limit. I don't know what they mean with the current limit. How much? No, but no. It has to limit always to 0.6. I don't understand this line. Threshold output. That's the resistance. Delay 10 milliseconds. Wow, it's still a bit of time, but 10 milliseconds is long. Still should do it. I don't know why it's wrong. Over current protection, over temperature protection, over voltage protection. I don't know what LO is. There's nothing a lot more. I followed the schematic. Did I? Check again. Yeah. Pin 1, 2, 3, 4, 5. That's correct. We have OCD. That's correct. That's 5 volt. Yeah, we have out. We have ground. I don't know. I really don't know. Let's try again with the oscilloscope. Damn it. Let me switch the oscilloscope so you can also view it. And my DMM and power meter are down again. Okay, my software is bugged. Osci capture. Okay, it captures the oscilloscope. Let me enable the oscilloscope. Tack. And let's try to debug. I'll also get a multimeter to actually test how much current goes through. 1, 2. Up. I'll put 10 amp. And let's get some leads. And let's see how much goes through it. 10 amp here. Now this is ground. And if we short it now, how much goes through. Nothing. It switches off. Okay, there's something wrong. The power meter, you see, it tells me that it uses 200 milliamp. But there's nothing going on in here. The short doesn't short. And maybe we do have to look at check with the oscilloscope. I need a ground connection. And the chip is getting warm. Why is the chip getting warm? That's the same issue we had. Remove the short. Same issue we had with when we were connecting with our, how is it called, our diode way of figuring out the overcurrent. So let's have a look at the output. This pin 1, that's the output. Super noisy. I don't have a ground connection of it. Here is a ground connection. This is the output. Still a tiny bit noisy. And if I short, I started to short it. So that's the voltage output right there. Now, if I short it, 0 volt, and it doesn't try to, well, a tiny bit tries to recover, but not a lot. It doesn't try to recover. And what here? Oh, here it does. We saw it. Yep. Ah, so it tries to switch on off all the time. Okay. This is why the 200 milliamp, but and because of the short, yeah, and here's okay, the normal auto trigger here, and because of the short, but why doesn't it report it to the host computer? What if I put it to ground? I want it to report to me. How long is the pulse? Let me check how long the pulse of the OCS is. That's this one. So it does go low. Up. Stop. This is 100 microseconds. It's very short. Let's remove the short. 100 microseconds. Maybe it's not long enough for the hub. Let's try to short here. So let's what if I short again now by hand? OCS, does it report to the computer? Yep. Overcurrent condition. It's because it tries to recover too fast. Let me have a look at the data sheet of this. This is in the EEPROM. You can set the overcurrent condition. Overcurrent. And I think it switches off. Does it switch off actually the output power? I think. I don't know. Let's check if it switches off the output power. So where is my oscilloscope probe? Awesome. Here. The enable pin is, don't remember. This one? Schematic. The enable pin is pin 4. 1, 2, 3, 4. This is pin 4. Let's see if this, let's switch the mode. Run. Does it switch it low if I short? It does it switch low. It does switch it low. And it tries to recover it and then it goes low. So the chip knows there's an overcurrent condition because it switches it low. Let's try to trigger on it. Yep, we can trigger. And how long does it switch on? It switches it on for 10 milliseconds. And after 10 milliseconds, I would like to have the second probe, second OC, to figure out what the correlation between the two signals are. Get another ground. You go here. And you go here. No, wrong one. 4, this one. Yeah, after 10 milliseconds, and I think this is from the, yep. After, you see, it switches it on for 10 milliseconds. After 10 milliseconds, we get 100 microseconds. This 10 milliseconds were from the data sheet. This is where we see it. Let's stop, and I want, yep. And then it switches off. And the switch off, when it switches is off, obviously the overcurrent is not there anymore. So it does protect. I don't know why it doesn't report. We'll have a look at the EEPROM. And I want to save, let me save this waveform. USB detected, yeah, print it. Yep. Okay, overcurrent sensing. This is done. Maybe I don't even need the external resistor, but I will still put it as non-connect in case it is not proper. Just because there's enough space. EEPROM. And the 10 milliseconds, right? The 100 milliseconds were from this, right? Let's check it again. Where did I see it? And when I saw it, like 10 milliseconds. Oh, that's the delay. But we saw 100 milliseconds. No, this is 10. Yeah, this is 10 milliseconds, so it corresponds. 1, 2, 3, 4, 5, 6. Yep. So this is what it corresponds, the overcurrent delay. That's correct. Now in the EEPROM. EEPROM interface. Here somewhere there's this overcurrent sense thingy. Let's do it by hand. Register, we don't care, product, device ID. Device ID, maybe I want to change it. No. The device ID is the version. We are at version 2, so I could, no, we're not, it's still version 1. It's not the board from version 2. Current sensing, so this works, it switches off here, timer. Overcurrent timer delay. What does this mean? Does it mean when you switch off power or when you report it? What did I do? vim eprom dot rb which register is it? 7. Configuration data by 2. Config 2 here. Timer 00. It's 0.1 milliseconds, but it's never that long low. It's only 10 how long was it? 100 microseconds? No, it is. This is what we saw. The 100 microseconds is the low low pulse, but it doesn't report. Why doesn't it report? After when does it report? What's this data sheet? It is still connected, and when I do by hand, when I connect to ground by hand, it reports overcurrent, right? Yep, it does. Why doesn't it do it when there is? Because it's too short and it's the minimum time before it reports overcurrent. So it does protect, which is the most important part, but I still want it to report to us. And currently it doesn't report to us. Why doesn't it? And I think the 100 microseconds is this is what's correct here. After 100 microseconds, it switches off. This is the overcurrent timer. Let's see where else now. No definition. OC timer is never mentioned else. This data sheet is, the more I read it, the more I hate it. Overcurrent timer. Yeah, the 2 definitions, nothing more. Doesn't say what it does. Here it also never tells that it switches off the power. Who write this piece of garbage? Specifications. Let's try to overcurrent. Let's see if there's overcurrent detection. Okay, it's not only detection, prevent it also. Overcurrent sense, overcurrent strap sensing. Okay. Ganged overcurrent sensing. No. Here. Select the current sensing on pole by pole. This is what we did. We support individually. This is correct. Overcurrent timer delay. I think this delay is after when it switches off. Why don't you report it? Do I have to contact microchip? How fast does it recover? That's the next interesting part. I'll zoom. Can I zoom into this just to show how long it takes? Yeah, this is the 0.1 micro. Yep. 100 milliseconds to 0.1. This is what we configured. What if we make it higher? There will be a longer short, but maybe it will report it afterwards. But here it clearly knows that there is an overcurrent condition. It just didn't report it. Yes, now I know. I want to know how often does it recover, or does it try to recover from this overcurrent? Where's the second probe? Where's my second lead? Here, this one. On this pin. No, on this one. Okay, it's a bit fluctuating and it's not stable. Stop. What's the time between both? Let's stop the overcurrent. Let's stop the shorts. 1, 2, 3, 4, 5. 100 milliseconds. After 100 milliseconds, it tries again to. Let's print this. It tries again to enable it. And then it takes 10 milliseconds to figure out it's not correct. It switches it back off, but it doesn't report it. Damn it. Do I want to change the EEPROM configuration and test it if we make it higher? Why don't you report it? You protect it, that's good. I want you to report it. There's no other specification, right? No, an overcurrent isn't there was nothing. At least it does protect it correctly. This is something good. So do you... I don't want it to overcurrent for too long. Well, this is the only solution we have. Let's make it longer. I need it. Oh, yeah, it doesn't put power on. Okay, so let's change the EEPROM and see if it fixes that. There's been one on my thing here. Timer. Let's get the data sheets. Yeah. That's the data sheet. EEPROM. Let's remap. We don't care about this. Here. Let's put it to 60 milliseconds. It's the longest. 1-1. Just to try. And which bits are this? 5 and 4. 3? Up. 3? This way? Ah, this is in bits. Okay. Ah, this is in bits. Right. So it's 8, 7, 6, 5, 4, 3, 2, 1. Yeah, this way. 4 and 5. Something is wrong here. No, it's not. It's correct. 4 bits, 4 bits. Okay. This is correct. Let's flash it. Up. Ah, it's too far away. I can't hold it and press play at the same time. Come on. Mini Pro. Okay, now it's 16 milliseconds. Let's... I don't want to lose my... Let's try it again. Bench. here. Run. And I will short it. Now we short it. And this is probably 60 milliseconds. Right? It's 6. It's even more. It's less. It's like 4 milliseconds. And did we add it to 4 milliseconds? But it doesn't report it. Does it? No, I don't see any reports. No reports. Stupid hub. 0, 1. I configured the wrong bits. 0, 1, 2, 3. Okay, yep. I configured the wrong bits. So it was 4 milliseconds. This is what I wrote. This is the correct one, but I think it will still not report. At least we know that this pulse corresponds to that. How fast? This is how fast it switches off after an overcurrent. Why doesn't it report? I don't know. Let's try with 16 milliseconds to see if it reports in this case. If not, then we just can't use this. Then I will remove the. Then we just can't use this feature. This overcurrent feature. So, program. Okay, that's done. Let's test it again. It's in a weird mode. Wrong bit, I think. I did modify the wrong bit. No, I didn't. 1 dynamic 0, 1, 1. 1, 0, 1, 1. And then 4 bits. Compound and reserved. No compound. What is happening? There's no short. So there's we're in a weird state now. Let's flash it again. I didn't set any of the reserved bits. Let's flash it again. Mouse. Here. This hub is so stupid. Damn it. Even the datasheet is wrong. If we put it back to 4 milliamps and 4 milliseconds, I'm sure it will work. Okay, it doesn't. I did change something. I don't know what I did change. Is there a short? No, there's no short. Because it doesn't have power. Okay. Maybe it was because it didn't have power. So let's try to change again. Now it's working. 1, 1 this way. Okay. Okay, I did something wrong. Let's check. Now we're 16 milliseconds. Does it report? 7 port hub detected. No, it doesn't. It needs to be a lot longer for it to report. I think the hub has an issue. Is there an errata somewhere for that? Yeah, it doesn't report anything. And if I run, it is running. And this is probably 16 milliseconds now. It's not. Is it running? It can't be running. I can't find it because I didn't do it. Yeah, now we're at 16 milliseconds. And it doesn't report it. I think it is designed for one chip in mind, as stupid as it sounds. Let's check the chip it was designed for. Let's put it back to 200 milliseconds, 200 microseconds, because this is safer. Don't want it too short for too long. Okay. Okay. Let's have a look. Full screen. So this one is behaving correctly. This is fine. That's not the issue. The hub is the issue. The EEPROM, we've modified what we could. I don't think there's anything else we can change here. We'll check it in the datasheet. But what I want to see here, in this evaluation board, they are using this one, this MIG 2027, 2026. Up here, what's your characteristics? How do you... I wanted to test something else also, but we'll test it right afterwards. First, let's have a look at here. Flag, active low, open rate, it's normal. Indicates overcurrent or thermal shutdown. Overcurrent condition must last longer than TD in order to flag. Yep, that's okay. And what is its TD? For the other one, it was 10 milliseconds. For the one we're using. What is his time? So something with here. TD overcurrent, 7 milliseconds. 3.5. What are all these times? Is there a diagram somewhere to tell me what this means? Voltage enable, that's the time on. This is rise and fall time. Time on, time off. We don't care. What other times are there? Time on, this is, we don't care. This is the race time. Output, turn on race time. Here. Short circuit response time. Yeah, microseconds. This is how fast it responds. over temperature threshold. Fall time. Oh, that's the output. So we don't care about this one. Nope, it doesn't say anything more. I think also this one, as soon as you switch off the overcurrent, it corrects. So I think the hub is bad. It's just a bad hub. I could contact turn off. Enabled into short. Ah, there we have a diagram. Enable, then we have this 3. Yeah, they said 3.5 milliseconds TG. And then they have this low. And the enable goes low, then it clears immediately the flag. So it's the same. It behaves exactly the same way. It's just that the hub is not reporting it correctly. The overcurrent condition. And there's probably no errata for this chip. Let's check. Microchip. Documentation. That's the data brief. I think this is the one we have. Is there a new version or is it the same one? Up. That's the new. Oh, I think this is a new. Wait. Does mine also look like this? No, it doesn't. There's a newer version. This is mine. This is the new version. Ah, but that's just a data brief. Okay, that's completely unimportant. Yep, completely unimportant. So next document. Oops, wrong one. Data brief. Data sheet. Ah, errata. Ah, there we have an errata. Let's see the data sheet if there is a new. No, it's the same. Let's have a look at the version. 2018 15198 1598C, and this is C also. So yeah, it's not this one. There's no new data sheet, but there's an errata. Family errata. Let's have a look at the errata. Implementation guideline, converting, PCB layout, don't care, USB device. No, we don't do a device. Bill of material, you don't care. Evaluation board, this is the EBIS model. Hardware design checklist. Woo, okay. Let's also have a look at this one. Silicon errata. Here. Hardware design checklist. Yeah. Seriously? USB signals. Does it talk about TVS diodes? That's what I'm using. Common mode strokes for USB? I didn't know that existed. Ah no, that's for galvanic isolation. Okay, that's not for you, for the USB signals themselves. Yeah, common mode choke for EMI reductions. Okay, I wasn't aware of that. Oh, I also never. USB. Here VBus detect. This is how we do it. Downstream. Port on, port off. Here is an input buffer which monitors our current then pull up resistor to the domain, so external resistor is not required. I want to try to test this. Let's go back to the bench and let's test this. I will remove the external resistor. Let's switch this off. Let's switch this off. I need to switch this back on. We will leave it floating because it's. We can remove it. And I will solder a lead here, this one, on the enable pin. Oh, let's remove this. Okay. Are you seeing what I'm doing? Yes, you are. Up. Okay, this is removed, and I will add here a lead so I can monitor it easily. Up. Using the oscilloscope. Check, check, and you go here. So you enable your power on. Power is on. Yeah. What if I short now? That's the short. Tack. Are we stopped? No, we're running. What is... Okay. Okay, we don't need an external... it's super noisy. But we don't need an external resistor. It works. Same thing, 10 milliseconds and then 10 microseconds. Yep. And it still reports nothing. Nothing is reported. Maybe it's... I have no idea. Well... The pin is ignored when the port... the pin state is ignored when the port is off. So what I wanted to do is keep it low for a long time. When the port is on. Maybe it reports when there's an overcurrent while it switches on and not while it switches off. Wow. An overcurrent event is detected if the state of the pin is detected as low. Okay, this is okay. When an overcurrent is detected, the port automatically moves to port off. Nice. Here it says, it doesn't say it in the datasheet, but it says it here. Come on. It moves to port off until the USB host can be notified of the overcurrent condition. No, that's not true. It never notifies me. Well, it never. If I keep it low, but else it didn't notify and it resets every 100 milliseconds. No, this is not true. To ensure bond cost, select the power active low open drawer input. If the, yep. So yeah, this statement, I don't know who wrote it, but this is not true. At least not in the hub version I have. Downstream Type C. Well, from when is this document? 2021. So it has been updated because Type C, when this was invented, this chip, there was no Type C. Ground on Earth recommendation. There it has said it. Okay, they have 330. I have 1K. At least I have a recommendation. That's good. Do I explain why? An RC filter. Yep. Minimize EN noise. Yeah, could put any value. Crystal connection. Yeah, this one. Why do they have this? Every microcontroller I know embeds this. R-bias, power supply, reset secret, reset instance, configuration option, configuration via EEPROM. That's correct. Configuration via Mac memory, recommendation diagram. Running generally no revolt of port settings. Yeah, we don't care. It's still interesting, and at least they did say here that it switches off. Port disable strap, port swap, we don't use that. Gang port, we don't use it. USB signal boost, we don't need. This is very specific. All the change logs. When is the late notes? Okay, When changelog? When? Yeah, release version. They released it completely new. Yep. Oh, here's a support page. I might contact the support page. But I think they won't be. Here, silicon errata. 7 pages. Okay. This, we don't care. We don't care. We don't care. We don't care. Nothing of these errata apply to us. That doesn't apply to us. Model 3, Model 4, USB does not detect downstream port in early. That doesn't affect us, and it has been created in 2014. This chip is old. It's ancient. But it's one of the few ones if you don't want USB 3. Yep. Yep. There is nothing about it. I'm sure if I... And now if I short it by hand, we will see it in the thing.